we can restart. It's my pleasure to introduce our next speaker, Professor Luís Costa. He is an associate professor with aggregation in physics department of Aveiro University. He is also a member of a research laboratory I3M, lastly evaluated with outstanding. His research focus on the characterization of materials, namely on electric and dielectric characterization, also in the field of microwaves for applications in electronics and electrical engineering. He has co-authored more than 250 of scientific papers, contributed to 7 books, more than 25 book chapters. His work has been cited nearly 3,000 times and has an index of 30. He has participated also with industry, in almost 50 projects, being coordinator of almost 20 projects. So welcome to Professor Luís Cadel.
Thank you, Silvia, for the kind presentation. So first of all, I would like to thank the organizing committee for inviting me, in particular Sofia, to come back to Morocco. So I represent this impedance spectroscopy, and even if the alarm was on, I promise that this is not dangerous, okay? This is not a dangerous presentation. Okay? So, I will do something very simple, okay? So, we start with some electromagnetic concepts, very, very simple, very basic, but are very, very important to understand the second topic, relaxation models, okay? Then, if you have time, some examples of equivalent circuits that can use to fit the data that can use using this impedance spectroscopy. And most important is a list of mistakes that everybody makes using impedance spectroscopy. Okay. So let's start with this very, very simple concept. It is impedance. Okay, impedance is a complex number. Okay, z asterisk. Okay. Is a real part, Z prime, and the imaginary part, Z double prime. Okay. Then, in certain, this is a macro property. So this is a property that depends of the size of the sample. Okay. If you have a sample like that or like that, okay, this is different. But usually we want to measure the micro properties that does not depend of the size and shape of the sample. So we calculate that we call permittivity, okay? And permittivity is also a complex number with a real part at one prime and the imaginary part at lower primes. In certain cases, let's say we measure this and you calculate this, okay? And also we can calculate another quantities, so the inverse of the impedance that we call admittance and the inverse of the permittivity that we call modulus, okay? But let's say we have one measure, this, and you can have 4 different quantities. All of them are complex numbers, real part and imaginary part. Okay? So, let's start with a very, very simple concept. It is electric field. Okay? So, here we have a charge, okay? Positive charge. If I want to know how is the electric field there, okay? I must put a charge positive plus 1 and to see what happens to this charge due to this one. Okay, if I put plus 1, plus, so this is rejected, okay? So the electric field is this vector, okay? If I want to see how is the electric field here, I put plus 1 here, okay? Then plus, so the electric field is like that, okay? That's why if I have a charge, the electric field is here, okay? It's like that, always, okay? So this is very simple. So then we can try what happened with the infinite plane. Okay, that's something like that. Infinite, okay? Okay, with charges here. Okay? So we have, for example, let's try to see what happened here. We put here plus 1, then we have this charge, okay? For this charge, it makes something like that, okay? Then, as this is infinite, okay? I have a symmetric charge this side, so we have something like that, always, okay? So, this is equal because this distance is equal to distance. So this is equal. When I sum, I have this. Okay? If I try to see what happened here, it's the same. Okay? I put a charge this side, the charge this side because this is infinite. Okay? And again, I have things like that and like that. I sum, and the electric field is always like that. Okay? So if I have something like that, infinite plane, my electric field is like that, okay? Always, in this side, like that, okay? Okay, and it's curious because in this case, if this is infinite, okay? It must be infinite. Why? Because if I must calculate the electric field here, I see a charge here, I must have a charge symmetric this side, okay? So, the electric field is always like that, and it is constant, okay? Does not depend of the distance of the plane, okay? So we can calculate this electric field, okay, very easy. And this is sigma divided by 2 epsilon 0. Sigma is the charge surface density, okay? So it depends of the charge. Okay, so now let's try. We have one infinite, okay? Then we put the second plane, okay? Oops. Okay, we have a second plane. Okay, this is one plane infinite, okay? And I put a second plane. Then I put plus positive charge, and here I put negative charge. So I have to try again, how is the electric field? So here, for example, I see the head plane, okay, positive, I put plus 1, it is like that, okay? Because it will reject. This one is negative, so it is like okay? But this is equal to this, okay? So this means this is 0, okay? This is due to the red one, this is due to the green one, okay? They are equal 0, 0, 0, 0, they are 0, 0, okay? And what happens here between the two planes, okay? I have here this plus, so plus 1, so it is like that, and this, because this is negative, this is attractive, okay? So this, I have this and this, they are equal, and now they are both, okay, to the bottom, okay? So I can sum, I have sigma, this is for 1, the second, so I have sigma divided by epsilon 0. So this is the electric field inside this capacitor, that we call capacitor, okay? So now we have to try to calculate the voltage between one plate and another plate, okay? So we have this equation, okay? The voltage is in the integral of the electric field, okay? And if this is constant, this is easy to go outside, okay? So it is very quickly A multiplied by T, okay? Because I'm integrating between 0 and D. D is the distance between the plates. So if I have, let's say, two parallel plates infinite, they must be infinite, okay? I have an electric field between them that is exactly this one, okay? And the voltage is this one. The electric field multiplied by the distance, okay? Then I can calculate the most important, this is called the capacitance. The capacitance is the charge divided by voltage, okay? We can make some calculus, very simple, okay? And at the final we have the capacitance is epsilon 0, this is the constant, constant of the vacuum, okay? A, this is the surface of the plate, okay? Divided by D, that is the distance of the plates, okay? And the charge that I can store in the capacitor is proportional to C. That means if I want to store a big lot of energy, I must increase C, okay? Okay, so to increase C, it has several possibilities. One, if I put something inside, let's say material, I must correct this. This is in the vacuum, okay? Or in the air, this the same, okay? If I put something inside, I must correct, and I have here epsilon prime. It was exactly the real part of the permittivity that we saw before, okay? The real part, okay? That means, if I want to increase C, I can put a material with epsilon prime very, very high, as high as possible, okay? Or I increase the surface. I increase the surface, that means I have very big capacitor that I cannot use in my mobile phone, for example. Or I decrease D. If I decrease D, okay, like this, as you will see, there are always problems. So the way it is always, in our case, increase epsilon prime, okay? So this is why usually we measure this very important property. Okay, so we have our parallel plate capacitor, okay, with infinite surface. And then what can do? We will try to apply an electric field, okay. Also here it is 0. Then I apply electric field. That means here I put a voltage, okay, with a source between these two plates. Then I create exactly this electric field, okay. And this, what happens when I put this? What happens? The dipoles. So a dipole, it's a mix of positive and negative charge. Okay, this is a dipole. Okay, and I can rotate these dipoles. Okay, so when I put in this parallel plate, for example, here I put plus and here minus. Okay, okay, these dipoles that are inside, they will align with the electric field. Okay, so let's see. For example, I see that. No. Okay. That means I apply this. For example, a strong electric field. All the dipoles are in the same position. Okay. Then I wait. Okay. And then I cut the electric field. Okay. The dipoles that were all of them in this position, they start to rotating, okay? But because at the hand, right, this like that, this that, they are in several positions. When I sum everything, it's 0. Okay? But when I have the electric field, they are like that. I cut, they start to rotate, okay? To come back to a final position, okay? But this takes time. It's not immediately, okay? So this is what happened here, okay? All of them are like that, then they start rotating, rotating at the end. Okay? They are randomly orientated, at the end it's 0. Okay? This is a function that we call polarization. The polarization, in fact, it's more or less the number of dipoles that are aligned with the electric field. Okay? So here, the polarization is maximum. Then it starts decreasing to the hand to 0. Okay? And this time that it takes to recover the final position, we call relaxation time. Okay? So in some materials, this depolarization is exactly exponential. Okay? If I see the number of dipoles that initially are like that, and then they start rotating, the number of dipoles that are still with the electric field decreases with exponential. So I can say that the depolarization is something exponential minus t divided by this tau. That is exactly the relaxation time. Okay, so this decreases. Okay, if I try with this logarithmic, okay, logarithm of this is logarithm this, okay. Minus t sur tau, okay? This is a straight line. Okay? If I make a graphic, log the polarization function as a function of t, I see exactly a line. It's exactly a line. Okay. This is called the Debye model. Okay. This is a model where the depolarization it is a perfect exponential. Okay. Then. Okay, then let's see what happened with this impedance spectroscopy. In impedance spectroscopy, what we can do is to apply, again, to these two plates, okay? I apply a signal like that, okay? It changes, like a sinus, okay? That means it is positive, okay? Positive, negative, okay? So that what happens? It is like that in this position. The dipoles are in this position, okay? Because I have plus attracts this minus, This minus attracts this plus, okay? So in this position here, in this side, you have this. Then I change, okay? I change, so I pass, I change, okay? I put minus, plus. What happened? This changes, okay? The type of changes, okay? And then I change, okay? What I'm doing in impedance spectroscopy, I start with a very low frequency, I make this, they rotate, all of them rotate. Then rotate, very, 1 hertz, for example. 1 hertz, that means one time per second. So it takes one second to make this. Then I increase the frequency. I increase, okay? At a certain moment, some of the dipoles cannot align because it's so quickly that some dipoles are almost dead, okay? And the number of dipoles is proportional exactly to epsilon prime. That's why epsilon prime decreases with frequency, okay? This frequency. So here, all of them can rotate. Then I increase. Some of them are lost, okay? At the end, almost they cannot turn with the electric field, okay? That's why epsilon prime decreases with frequency, okay? Then epsilon double prime, that you saw that it was the imaginary part, you can calculate. This is not important now, but you can believe that it's something like that. Okay? It has a maximum exactly in this inflection point. Okay? When I see this in this point, epsilon double prime, I have a maximum. Okay? So we can prove this using Kramer's-Kronig relationships, but it's too much complicated, so it's not important. So, what is important? Well, this is what happened, okay? Here, in the beginning, low frequency, epsilon prime very high, it decreases, this increases. So we change in this representation. We try to do epsilon double prime as a function of epsilon prime, okay? So this red one, okay, this is low frequency. So epsilon prime is very high, okay? It's very high, it is this point here, okay? This is the red one, okay? You see, epsilon prime is very high, and epsilon double prime is 0, okay? 0. So we have this point, okay? Then we increase the frequency, epsilon double prime starts decreasing, okay, decreasing, so it decreases on this side, it decreases, and the epsilon prime increases. And then I have a maximum here, okay? So I have something like that. The green point is this point. So and then epsilon prime decreases, epsilon double prime decreases. So they both decreases. At the end, I'm here. This point is this point, the yellow point, okay? So that representation and this are two different representations, but with the same information, okay? And this point, it is this point, this maximum, that we call the relaxation frequency, okay? That is the inverse of the relaxation time, okay? So we have always something like that, okay? So here it is low frequency, here it is high frequency, okay? That's why here we call epsilon static, because static is low frequency, 0 frequency, and here we call epsilon infinite, very high frequency, okay? So we have something, so frequency increasing from the right to the left, okay? So we are seeing this in epsilon, but we can make the same in Z, okay? In impedance, it is exactly the same, okay? Okay, so we saw the bimodal, exponential, okay? Then we use Fourier transform. We can pass from this time domain to frequency domain, okay? So it's more or less complicated, but at the end we have this equation. This is the same equation, but in frequency domain, okay? So epsilon, okay, that is function of frequency, okay, is epsilon infinite, epsilon static minus epsilon infinite, what? I omega tau, so I complex number, okay? Okay, so this is true for the Debye model, okay? So then we have this, then we have to try, so we have here this I in the denominator, okay? I want to pass to the bottom, to the top, okay? To have epsilon prime, epsilon double prime. That means I want to separate epsilon prime and epsilon double prime. So I multiply this by the conjugate, okay? 1 minus E omega tau, okay? So we have this, okay? We divide this, so, and we have real part, okay? And imaginary part. Again, epsilon infinity, epsilon very high frequency, static, frequency 0, okay? Okay? Relaxation time, okay? So I have already separated epsilon prime and epsilon double prime. But this is true for Debye model, okay? Only for Debye model. Okay. So then I make some small calculus and I obtain this very important equation. What is this? Epsilon prime minus this square plus epsilon double prime minus 0 square equal to this square. This is the equation of a circle. Perfect circle, okay? The radius of the circle is this, okay? So, I know that I have a circle. The radius is exactly this, okay? And the center of the circle is this 0, okay? So, this is the center of the circle, this is the radius. So the center, epsilon static plus epsilon infinite divided by 2, 0, okay? So, if this is 0, this means that I'm here in this x, exactly in the x. So, if I am in the Debye model, when I make this representation, epsilon double prime as a function of epsilon prime, I must have exactly a circle, and the center of the circle must be in this x. Always, exactly in the x, because here we have 0, okay? Minus 0, okay? So, then, what happened in most part of the materials? The Debye model doesn't work, okay? So again, we have the Debye model here. So we have another one we call co. So we have here one exponent, 1 minus half, okay? Only this part, okay? We put this part with this, okay? Or I put all the denominator, okay? With the exponent also. This is called Davidson. And more complicated, that is, let's say, mix this, okay, this and this, okay, that we call average again, okay. But let's see the most important, Debye, and what happens when I have Debye. So I know Debye, it's a circle, and the center of the circle is exactly in the x, okay. So what happens when we have so this is the Debye, okay. Debye, so the circle is here. Okay, so see the circle, this angle is 90 degrees, this angle is 90 degrees, exactly. When I put the code, so when I put this exponent, okay, what happens? The circle goes down, okay? And this angle here is 1 minus, no, it is alpha multiplied by 90. For example, if alpha is 0, okay, if alpha is 0, this equation is this equation, okay? So if alpha is 0, that means this point is here. So it's okay, this is this, okay? Okay, so when I have my data, I make the representation, I see, okay, if the circle is this one, the center is here, I use the Debye model. If the circle is like that, the center is here, I use code. If the circle is deformed, okay, this is called Davidson. Okay, this is a little bit more complicated. Okay, but we try this one. If it doesn't work, this one. If it doesn't work, this one, and we have a fourth one. Okay, but usually in most of materials, Debye doesn't work. Okay. Okay, so let's see what happened with equivalent circuits. In the Debye model, the circuit is RC parallel, okay? Exactly RC. So if I have this RC, okay, so you know the impedance of the capacitor is 1 divided by I omega C, okay? The impedance of the resistance is R, doesn't depend on the frequency, okay? And for example, if I try to see what happened for omega equal to 0, that means the static, okay? Very, very low frequency. That means if this is 0, okay? If this is 0, this is infinite. Okay? Okay? So, we have this in parallel, okay? You can calculate. Let's see what happened for very low frequency and very high frequency, okay? Let's say 0 frequency, infinite frequency. So, let's see. Okay. 0 frequency, okay? 0 frequency. This is infinite, okay? So, there is nothing here. This is an open circuit. So, this circuit is simply R, okay? When I increase the frequency, okay, that means when I go this side, for infinite frequency, as the okay, this is infinite, okay? So this is 0, okay? So the impedance is 0. See, if it's 0, it is a short circuit, okay? So in this case, 0. 0 parallel with R, it's 0, okay? So what happens? What means exactly? For very low frequency, we have R. For very high frequency, I have 0, okay? So this means that it is exactly this, okay? This is exactly the Debye model. It starts here, R, the frequency increases and goes to 0. So this model, it works perfect for this Debye model, okay? So for example, then let's try to see if I have something like that, for example. Sometimes I have, okay, a circle, it doesn't go to 0, it goes to this point. So what can I do? Let's see this circuit, okay? For omega infinite, okay? 0, for omega 0, okay, this point, okay? This is open, okay? Okay, so we have this plus this, okay? This is the sum of both, okay? When omega increases, okay, this is a short circuit. 0 parallel with this is 0, so it's 0 plus this, okay? So I have this here, okay? So that means if I have a circle that is like that, not here, I must put this the resistance, okay? So we have always a lot of possibilities. For example, if you have something like that, one circle, no 0. So what happened? One circle, RC, one circle, RC, and this is the thing. So it's very easy. We can see exactly this. Okay, I can decide very in principle, very easy. How many RCs I can put and so on and so on. What's the problem? When we make these measurements, usually we wouldn't have this very nice. Okay? We have something like that. And even you have that, something like that. Okay, we can deconvolute, separate the two circles. But sometimes we have something like that. So we don't know. Must I put 2 circles or 3 circles or 4 circles? What can I do? So that means I need another information because impedance spectroscopy is not enough. I must have or SAM or X-ray or Raman or FTIR or so another information to decide. Okay, this is 2 circles or 3 circles. Okay, and this is also important. Okay, okay. Then finally. The list of mistakes. Okay, let's say people that works with impedance spectroscopy, everybody makes at least one mistake in his life, but for sure more than that. Okay, in particular me, that I work in these kind of problems about 35 years. So 35 years. It's a lot of time. It is enough time to make mistakes. Okay. So let's see some of the very common mistakes that we see even in papers today, okay? So one of these is this, okay? This we calculate this capacitance, parallel plate. If this is not parallel, okay, this is parallel plate. If this is not parallel, the electric field is not constant. inside. And if it's not constant, we cannot do this. That means we cannot put the electric field outside of the integral. So this formula doesn't work. Okay? So this is one very, very common mistake. So we must be sure that the electrodes are absolutely parallel. Okay? So, second mistake. If D, this is true for infinite. Okay? Infinite, that means there's no infinite. Okay? I cannot make an infinite plate. Okay? But I can imagine that it's infinite if D is very small. Okay? If this D, okay, is very small, but the distance compared with this surface, this plate, okay, I can say, okay, this is a parallel plate capacitor, this is infinite, almost infinite, and it works. But if this is not true, we have this leakage field here, okay, and this is no more valid. So, it doesn't work, okay? Another one, this is also very common, the time measurement, okay? If you want to measure the conductivity, for example, I apply a field, okay? And I cut, for example, and I see the depolarization, okay? Okay? Okay. If I measure, if I have this blue curve, for example, if I measure here, okay, this is not constant no more. So I must see, okay, the current, if I want to measure the conductivity, because I have my sample, I put on my voltage, 100 volts, and I have tick, and then zzz, okay, and then here, okay, I must see that current is constant. If this is not true, very common, very, very common, so we must know exactly how the current decrease to attain the final value. I put it easy, porous. Another problem. If I have porous here, usually we put silver ink here, okay, to make the contacts. If I have a porous, the silver go here, okay, inside. This distance decreases, and have short circuit. It's also very common. That means if I have a porous material, I cannot use this kind of electrodes, okay? I have another solutions, okay? Also a very common mistake. Another mistake, if I measure, for example, the resistance of this sample, and this resistance is very small, for example, very conductive material, actually I measure the resistance of this wire plus this and plus this, okay? If this resistance is very small, this is very important, okay? In my case, I usually measure glasses and polymers composites, not very conductive, so I have not this problem. But if you have a very conductive material, okay, I must be careful with the length of this wire that also they contribute the measurement made by this equipment. Okay? This is also thousands of times, thousands of times, and thousands of papers. Okay? You remember the circle? The perfect. This is a divide. Okay? Exactly a divide. Okay? Because you see, this distance is 5, 5, 5. Okay? Okay? So this is a square. Okay? This distance equal to distance. So here, if the scale is 10, here, okay, must be 10. Okay? Okay. If I have a square, the scale here must be the scale here. Okay? For example, this data is that data. Okay? But, okay, you see, this is 5 here. Okay? Then I compress this, and I have this. Okay? It is exactly the same. This is really divide. And if I see only this one, okay, this is not divide. This is called code. because apparently the center of this is here. Okay, I can make something like that. Okay, and so this is the most common. To finish, I show you this curiosity because when we try to avoid mistakes, sometimes we create a mistake worse. Okay? So, and I contributed some years ago, many years ago, I made my contribution with a quite interesting mistake, okay? Because I tried to make this measurement, okay? Exactly this, I put it, and cut. And then, for example, in the hair, the electric field maximum, okay, that I can have, let's say, it depends, but normal conditions, humidity, temperature, it's about 1 megavolt per meter, okay? Electric field. And 1 megavolt per meter, that means if I have 1 meter, okay, this is 1 meter, I can put 1 megavolt, okay, 1 million volts, okay, between these points, and it's okay, okay, 1 million. If I decrease the distance, for example, 10 times, 1,000 times, 1 meter to 1 millimeter, I must divide also the voltage by 1,000. I'll say I have 1 million, 1 megavolt, so I can put in 1 millimeter, I can put 1 kilovolt. Okay? So I have something like that in the air, 1 millimeter, I can put 1 kilovolt. If I put 2 kilovolts, okay, I have a discharge. Okay? Here, if I put 1 mega, it's okay. If I put 2 mega, I have a discharge. Okay? So, I was trying to make this measurement, and I was thinking, okay, it's important to have this D very small. Okay? Okay? I don't want this leakage. So I must have this D very small. And what was the problem? Okay, something important. Here, okay, in the hair, I have 1 kilovolt in 1 millimeter, okay? If I put something inside, okay, in my case it was, I don't remember, a material, polymer or something like that, I can increase, okay? So I can pass from 1 kilovolt to, for example, 2 kilovolts, okay? So I know, okay, I can put 2 kilovolts here, okay, but in 1 millimeter, okay? So the problem is that here, for example, this distance must be lower than this one, okay? So if I have something like a disc here, for example, 1 centimeter, this distance must be almost 0.1 centimeter, okay? Let's say 1 millimeter, okay? If not, we have this. So what happened with my case? I had a very small sample. So I had here something like 0.5 millimeters, okay? So I decided, okay, 0.5, I want this very small, I put 0.05, okay, to decrease, to avoid that. And I forgot that if I put 0.05, I cannot put 2 kilovolts, okay? 2 kilovolts, it was for 1 millimeter. If I pass to half millimeter, I must divide the voltage by 2, of course, okay? So I forgot that. So I put this very nice sample with this, okay, 0.5 centimeters, okay, and here 0.5 millimeters. When I put on 2 kilovolts, okay, 2 kilovolts, so immediately I have a discharge between the two electrodes, okay, and this discharge, it's a short circuit, so it destroys the sample, but this is not important. But at that moment, many years ago, the protections of the sources voltage forces were very bad, and what happens? I put 2 kilovolts in a short circuit, in zero resistance, okay? So it was goodbye voltage source, okay? So a real mistake. So to avoid this mistake, I produce a real more dangerous mistake. So sometimes we have to think, okay, do not create a mistake, a stronger mistake, to avoid a small mistake. Okay? So, thank you for your attention.
We have time for one or two questions.
So instead of decreasing the distance, you can increase the dielectric constant.
Yes, of course. But the problem is, in known materials, when I increase epsilon prime, epsilon double prime increases also. Okay? It's normal. And epsilon double prime is proportional to the conductivity. So if the conductivity increases, the current that passes through increases. If the current increases, the temperature by Joule effect increases. Okay? And this is the problem. We must have a compromise. You must increase epsilon prime, but do not increase too much epsilon double prime. And this is the big physical problem.
There's something for energy harvesting. It's important to try to increase the dielectric constant so that there's more charge across the electrons.
Yes, yes.
Yes, please.
Thank you for your presentation. I have a question about the materials which present high anisotropy. If you have worked with this kind of materials.
So we made measurements exactly in the anisotropic materials, but in this case, we made this in, let's say, high frequency, okay, microwave frequency. Why? Because we use a waveguide, okay? And in the waveguide, the electric field is very is like that always, polarized, very, very. So it propagates inside this waveguide like this. It is always like this. Mm-hmm. If I want to measure a measurement, I made this in some
other axis.
I put my material here and I rotate.
Rotate the waveguide.
No, I rotate the material.
Okay, the material.
I have the electric field always like this. My material anisotropic. I make a measurement here, okay, and I calculate epsilon prime, epsilon double prime, and I change 90 degrees, and I calculate epsilon prime, epsilon double prime, okay. And if it is an anisotropy, it is absolutely different. Okay, this is interesting because we try to do this to check beef, okay, stick, okay. When the stick is in good conditions, we have these fibers, okay?
Yeah.
So it's very anisotropic. So I took a beef, I put the beef inside my cavity, I measure the beef like in this position and in this position. It is completely different.
Yeah.
Then I wait 8 days. So it smells not very good. And then these fibers are cut, okay? The fibers be cut in the beef. So it becomes more isotropic. So I make the same measurements, and in this case, because it is very, very bad conditions, I made in this position, it is also almost the same. So I can decide with my cavity, I can go to the market with my and to test to see in the beef the quality of the beef, but for sure with the smell it's better, it's easier.
Thank you.
One more question, yes.
Thank you very much, Professor, for your nice talk. So, my work is about hydrogen production, and what we face in production of water, we have some diffusion, and sometimes of species to our electrodes, impact electrolytes. And this is when sitting, for example, we give Warburg in our model set. So can you, Professor, please talk about that?
I never made this kind of these materials, but for sure it works also. For sure you can see the diffusion between membranes, for example, using also impedance spectroscopy. But I never tried with these materials.
Sure. There is another question over there.
Just a question. For battery, the equivalent circuit, I can recognize it the same way. But I just wondering if for batteries exactly we can use the bare model or
but,
other kind of model?
But yeah, I saw some articles in this kind of materials, and I think that the equivalent models are almost known. Okay? So we know exactly what happens. Okay? And we see something like that, and you can decouple weight 1, 2, 3, okay, ground boundary and boundaries and electrodes and things like that. Okay, this is known. And in batteries, it's one of the methods quite interesting to check batteries. It's that's spectroscopy.
Right now they're using the terminal model.
But the model usually it's not divided, for sure. It's rare. Divides because the problem is divide model. It means that you have the dipoles. They go exponentially. This means that this dipole does not interact with this dipole. This dipole does not see these dipoles. Okay, in most materials, they are connected some way. Okay, so when this turns, this affects this one, and so we have no more divide.
To have a distribution.
Yeah.
Another one. So I think we will stay here.
Be careful.
The last
alarm.
question. And you can discuss outside. Yeah.
Yeah.